this week's lecture. I'm just going to do a few smaller topics that aren't sort of central to this course, but are interesting from a theoretical perspective, and we'll just skim across these a little bit rather than doing them in as much depth as we could. So the first one is programming with propositions. So we talked before about how propositions are first-class things, really. So that means in theory you can write functions that take propositions as arguments, which we've seen. So lots of our theorems were things that took propositions as arguments and returned proofs of propositions as arguments and returned proofs of other things. So there were functions that returned prop. But we can write these things in a programmatic way as well. So instead of thinking of it just in terms of logic, we can say, well, we can write a fixed point thing like this in that returns a prop. So you can sort of calculate with props as well in some sense. So what's the deal with this example? So imagine that you've got lists of things, lists of A's in this case, and you want a proposition that expresses the fact, well, the claim that a given element of A, so X in this case, is an element of that list. So somewhere in that list, X appears. And so if I gave you a particular list, you could write this proposition down, right? You would write down X is equal to the first element of the list, or X is equal to the second element of the list, or and so on all the way down. Okay. So what in is doing here is recursively producing the proposition for some arbitrary list and some arbitrary X. Okay, and it's doing it in a recursive fashion that's pretty familiar. So it basically says, well, if the list L is empty, I should mention, sorry, before we start this, you'll need to add these imports to the file, I think, to get this to work, because this is using list notations and things. So add those if you're running this. Okay, so if we need to say, well, list L could be empty, in which case X is definitely not part of this, so we return the false proposition. Right? We can't ever show that X is a member of an empty list. But if the list is not empty, we can break it down into the head and tail like we've done before, and we can say, well, one possibility is the head, X prime here, is equal to the X we're looking for. And the other one is that X is in the tail somewhere. And we can connect these with a disjunction, so we either have one or the other, or possibly both, if X appears more than one time in the list. Okay, so we can define this, and it's just a simple recursive function in the usual way, and Coq needs to be able to show that it's going to terminate and all those sorts of things as before. But the big difference is that this is going to give us a prop as the result, not a nat or a list or something like that. So we can use it in this sort of context. So we can say, well, this thing here is going to compute a proposition that 4 is an element of the list 3, 4, 5. Okay, and one thing that we could do, just to make this a bit more concrete, is if we say check that, you see that's a prop. Okay, let's see what happens if we compute that. Right, so what that's doing now is running the in function to get the value, the prop value that is the result of that function. So you can see there it is. It's 3 equals 4, which is the thing we're looking, the first element of the list equals the thing we're looking for, or the second element of the list is the thing we're looking for, or the third element of the list is the thing we're looking for, or false. So there's always going to be a false at the end, right, which terminates everything, and you get exactly the number of conjunctions as the number of elements in your list. So if we deleted the 5, we now only get 2 conjunctions because there's only 2 elements to compare to. Okay, but because this is a prop, it works as a type essentially, so we can use it. So it's now a goal, right? So if we do simple here, it's going to turn it into it's going to run the function to generate the proposition. And now we have to look at this. So remember, with disjunctions, we have to decide which part of the disjunction is going to be the bit we're going to try and prove. And if we look at this, well, we're not going to be able to prove 3 equals 4. We probably can prove 4 equals 4, but not 5 equals 4, and definitely not false. So what we need to do is somehow focus on the second part of the disjunction. Okay, so the first thing we can do is pick the right-hand side of the first disjunction. So remember, this is going to be bracketed in a particular way. So that gives you it's going to be bracketed to the right. So the first disjunction is going to be at the top of the tree, if you think of it that way. So when we choose the right, that bit disappears, and we end up with the simplified version with just the two disjunctions. And now we can choose the left to get rid of the bit that we definitely don't want. And now we've got an easy 4 equals 4 proof. So this is the first example we've seen where we've had a nested disjunction where we've had to pick the path down to the thing that we want to prove. Okay, but the new thing is that we haven't stated the property here that we want to prove. We've computed the property by using this fixed point function, right? This is a very powerful idea because it means that the theorems can be in some sense generated by the data that we have. Okay, not fixed. So this is another exact use of that. So in this case, it's saying so this is kind of a funny thing to assume. This is for all n such that n is in 2, 4. In other words, n is an element of the list 2, 4. For all of those, there's another natural number that's half of that, basically. So n is 2 times n prime. In other words, every element of this list is even. Okay. So if we do the simplification, that will turn the in, so this in here will turn into a 2 equals n or 4 equals n or false, right? Comparing the thing we're looking for, which is n, with the elements of the list, which are 2 and 4. And then we can sort of move into intros mode. Now they're doing this highly nested intros here, so I'll just sort of do that one step at a time. So if I do intro of n first, I get the natural number, so that's easy. The next thing is a disjunction, right? So it's going to be this piece or this whole thing here, right? So if I do the next bit, which is sort of like this, so let's call that I or something, right? Then let's leave that. So that's ignored all the other things, right? But we don't want to ignore the other things. We want to keep them around as well. Well, it doesn't ignore them. They're in the case for this goal. Okay. So what this is doing is saying, well, for the next level of disjunction, call the thing H as well. And then what's happening with the empty list? Well, that's going to match up to the false case. And there are no variables to do there, and it's going to discharge that in one go. Now I've got the wrong number of brackets. There we go. Okay, so if you don't like using the nested intro syntax, you don't have to use it. You can intro everything in a simpler way, but they tend to get a bit tricky in some of these examples. Okay, so what are we going to do in the first case? So notice there's two goals. Go back one step. So notice there's two goals, and what we'll find is that in the first goal, n is 2, because that's the first element of the list, and in the second goal, n will be 4, because that's the other element of the list. So we've reduced this to one goal for each of the elements of the list, which is what the theorem says, that this holds for everything that's in that list. So we have to prove this theorem, this goal for all of those. So if we do that, we get to here. Now we've got to find something where n is 2, and 2 has to be equal to n prime plus n prime plus 0. So that says, well, if we choose n prime to be 1, then we're going to get what we want. Right? So we can rewrite with the n being 2, and then it's a little simplification, we'll do it. So in other words, what we're doing here is we're having to tell the system which particular n prime to use to make the theorem hold. We've got to find a witness. And in this case, the witness is always going to be half of the value of n. So the second case works in the same way, except we pick 2 because the number we're interested in is 4. Okay, so there's a lot more in here about that sort of thing, and there's a bunch of stuff here about, yeah, you've got to make sure everything is obviously terminating, and basically that limitation is one of the reasons why people don't use computing propositions like in very often. They're used a bit. In the next chapter, as I say, we'll see a more flexible way of defining propositions using inductive data types like we've used before, which doesn't require the termination thing, but comes with some other limitations that mean it's a complementary technique. We'll talk about that next time. So I won't go through these proofs, and there's also another one for all. So this is kind of the thing that's intended to be, well, there's a list and there's a predicate essentially that you can use on T's, and all says, well, that predicate holds for all of the elements of the list. So that's good practice to try to do that if you have time. And I won't spend time on these things. Applying theorems to arguments we've actually used a bunch of times already in the course, so I won't spend too much time on it. To get this plus com to work, you'll have to import require the induction chapter. So all they're really telling us here is stuff that we've used before, which is that when you have a theorem like plus com, what you essentially get is a function that takes the two nats that you're interested in talking about and gives you an equality between the things that the theorem talks about. So in the example down here, they're proving commutativity with 3 things by using the one with the 2 things. And the issue that they've got is when they get to this point, they rewrite with plus com, and then if they rewrite with plus com again, which they want to do, it just undoes the first one, basically. So the problem is you have to somehow target the plus com rewrite to which particular plus you want to commute. So one way to do that, which we've seen before, is to use an assert to actually state explicitly we're interested in m plus p equals p plus m, and then use plus com to prove that. And the other way, which we've also seen, is to not rewrite with plus com, but rewrite with plus com where one of the arguments, or maybe both the arguments, is specified. So in this situation, if I rewrite with plus com, it's just going to undo the first one. But if I rewrite with plus com m, that will fix it to finding a commutative thing where m is the left-hand side of it, which will do the right thing. Okay, but we've seen a bunch of examples of that. This one, don't worry about that one. So this topic here about Coq versus set theory is really about set theory is sort of conventionally regarded as the sort of foundation of mathematics. Everything can be formulated in terms of sets and sets and sets of sets and things like that. Coq is different because it uses this sort of inductive construction sort of idea. So it's really a different foundation, if you like, for mathematical types of things with strengths and weaknesses and so on. It turns out that there's not necessarily an equivalence between things that you can state using normal logic with set theory and things that you can define in COC. And the one we mentioned before is the excluded middle thing. So in normal logic and set theory and things, you know that something is true, or a proposition is valid or it's not valid. There's no other possibility. So you can often prove things by assuming assuming those two things and showing that one of them leads to a contradiction. In this system, you can't do that because you can't just assume that. It might be that you can't prove constructively that the thing is true or not true. And if you can't do that, then you just don't know. Now, it turns out in the theory of all this stuff, there's some things that are not provable from the core of Cox logic, right? And one example is this thing called functional extensionality, which is essentially saying that if you can show that two functions produce the same result for every possible input, then you can say the two functions are equal. Okay. And it turns out that you can't just prove that from the normal Coq foundations. But it turns out also that if you assume it, nothing goes wrong. So that's what this axiom thing does. It basically says, I'm defining this thing and I'm not requiring you to prove it. Basically, it's like admitted, but it's more sort of indicating I meant to do this. It's not something I just forgot to go back and prove. It's something that I'm not going to prove, but I'm going to assume, essentially. Okay, so you can use this for things like, well, here I've got a function. Basically it says, well, plus the function we've defined before is equal to the function that takes two numbers and uses the plus symbol on them. And without functional extensionality, that's kind of hard to prove. Well, it's harder to prove. So here it's, I can use functional extensionality, which basically puts the for all out the front. Right, so to prove that these two things are equal, all I have to do is prove that they produce the same result for each natural number. Okay, and I need to do that sort of twice because I need to introduce m and n that way. So I end up with this thing, and now I can say, well, do the commuting thing, and then I'm done. Okay, so the important logical thing is we can't prove this yellow thing up here, orange thing, whatever, but it's safe to assume it. Now, what most people in these systems do is they only assume it when they really need it, because it's generally a dangerous thing to just assume things and then use them in proofs, because if they're not actually true, then you've introduced a logical fallacy into your system and you can prove pretty much anything. Okay, so let's just go back to the other thing for a minute. Propositions and booleans. So let's go over that. So I mentioned this before, so I think you should read this section and sort of just practice with some of this. But the idea that a proposition sort of represents truth and falseness in some sense, but that's what booleans do too, true and false. But they're different notions, and the Boolean one is well, we can compute the true or falseness, whereas the capital T true and capital F false are propositions that we can reason about in a logical sense. And so let's see, the example that they give here somewhere. Yeah, so down here there's an example where they say, well, if you know that BQ nat NM is equals true, it's a bit annoying to use that in a proof because you can't rewrite with it or all those sorts of things. So you don't actually want to know that the BEQNAT function computes true in this case, you actually want to know that logically n equals m, which is the proposition version of that. Okay. Now, in many cases, you can convert backwards and forwards between them. So this one here, BEQNAT true if and only if, says that. It says if I can run BEQNAT and get true, then it must be the case that n1 is equal to n2 and vice versa. Okay, and the proof's pretty straightforward. So just bear that in mind as you're going forward, is that the Booleans are not the same as the propositions that are true and false. So it's sometimes hard to, when you say true, what do you mean, the Boolean true or the proposition true or false or whatever? So you have to be a bit careful with those sorts of things. Okay, so I'll let you read that. And the last thing I want to talk about is the constructive, classical versus constructive. And that's, again, basically what I was saying before. So there are some things like excluded middle, which is that P is true or not P is true, that you can't prove from the basis of Cox's logic, basically. Okay. Again, you can actually state it, and you don't get into any contradictions. So there's a bit of discussion about that sort of thing, which if you're interested in logics and those sorts of things, I would encourage you to have a look at it. We won't spend any real time on it. The thing that if you want to spend a lot of time, but it's really good exercise if you can do it, is this 5-star one. This is really essentially saying that there are a bunch of things. So excluded middle is one, and then these things that are all equivalent to each other. So it turns out that if you assume one of these, you get all the other ones, right? And this exercise is about saying, if you assume excluded middle, you can prove Pierce, right? But these are all in the class of things that can't be proven directly by Coq from basic principles, but are safe to state if you are working in a sort of more classical world. Okay, so I think I'll stop there. So that's the end of the week 5 lectures. Hopefully it hasn't been too mind-numbing at this stage, and I'll talk to you in the discussion session about any confusions and things you have. So talk to you then.